week 3 of interactive live sessions for the course called Fundamentals of Convective Heat Transfer offered by NPTEL. The course is being instructed by Professor Amaresh Dalal from IIT Guwahati, and I'm a PhD scholar at IIT Madras. My name is Debjit, and we will be solving some tutorial problems related to the course together, and we will try to have as much as interactions throughout these sessions as possible. So with that, let us begin. So this is question number 1 of today's session. Question number 1 says that for a boundary layer flow over a wedge, if the wedge angle is negative, then the flow accelerates along the surface. So there is a statement given, so you have to decide whether this statement is true or false. Once you have figured that out, you can type in your answer in the chat box, or you can even unmute and tell the answer. So I'll repeat the question once again. The question number 1 is for a boundary
Sir,
layer flow.
slide is not visible. It's on first slide only.
Visible? Oh, I'm so sorry. I checked it once anyway. I'm stopping and resharing once again. Okay, so what about now? Are the slides visible now? Hello, are the slides visible now?
Yes.
Okay. So sorry for that glitch. Anyway, I'll repeat question once again. So there is a statement given whether for a boundary layer flow over a wedge, if the wedge angle is negative, does the flow accelerate along the surface? Is that statement true or is it false?
Hello, sir. It's false.
Yes, correct. So the correct answer is it is false. So what actually happens is, let's say if we have a flow like this, and a negative wedge angle means an expansion of this sort. So this angle is a negative wedge angle minus beta. So this is minus pi beta. So if this is negative, then there is an expansion, and as a result there is the pressure gradient is an adverse pressure gradient. So if we take x along this direction, so dp dx would actually be greater than 0. So as a result, if there is a flow coming from this side, that flow would experience a deceleration, and that is why the statement given over here is false. It won't experience an acceleration, rather it would experience a deceleration. So that is why this statement is false. Moreover, in situations like this, what happens is there is a risk of flow separation. So as a result, during engineering design of such systems, this has to be kept in mind. So this was a simple one. Moving along, we move on to question number 2 of today's session. So that says, question number 2 says, okay, someone has a question. Yes, you can unmute yourself and ask.
Sorry, sir, we are unable to see your explanation figure.
Sorry, can you come a bit louder?
Sir, we are unable to see your explanation figure also.
You're unable to see my figure. Is this figure visible or not visible?
Explanation figure.
Debjit sir, have you drawn something on the board?
Yes.
No, that is not visible then.
That is not visible? Oh.
Yes, sir. That's what happened.
This time I'm not clear.
Yes, it's visible now.
Okay, can you give me a moment? I'll be back again. Had a ball. আরে আমার ক্লাসটা চলছে রে।
Yeah, it's visible, sir.
It's visible now, right? Okay.
Yes.
So I'll repeat the explanation once again. So as it happens that if it's a negative wedge angle, that means the flow would be through something like this, something sort of like a diffuser. So the area of flow would increase, and as a result, there would be a deceleration of the flow. There would be a positive pressure gradient and adverse pressure gradient, so to say. So due to this, there will be an effectively a deceleration of the flow, and as a result, there might be flow separation as well. So uh, as relevant to the question, the statement given is false. The flow does not accelerate along the surface, rather it decelerates. That is why it is false. So I hope that clears things up. We will move on to question number 2. So question number 2 says the pole burn analogy relates what? There are multiple options given. So option A says fluid friction and pressure drop. Option B says fluid friction and heat transfer. Option C says heat transfer and mass transfer. And option D, none of the above, which means none of the above given options are correct.
I'm sorry, again we are unable to see the question. We are unable to see the question.
Sir, we are on question 1 only.
Oh my god. Okay. Which is today's session. I'm really sorry, and I'm not sure why are they happening. Question number 2, is it visible now?
Yes, yes. Sir, can you go on a slideshow mode?
Is it not in slideshow mode right now?
No, on the.
The answer is B, sir.
Okay, give me a second. I'm trying to. I'll share my entire screen, that way I know. Okay, so what about now?
Fine, fine.
Fine, right?
Perfectly fine.
Okay. So we'll start again from the
The
top.
answer
So
is B, sir.
answer is B. Okay, someone says answer is B. What about others? Okay, there is a
Yes, answer is B.
text message saying answer B. Okay, and everyone is actually correct. So Cold-Burn analogy relates the fluid friction with the heat transfer. So if we write down what Cold-Burn analogy tells us, that is the local Stanton number X multiplied with sorry, local Stanton number x is actually into Prandtl number to the power 1/3, that is equal to 0.332 sorry, no, this CFX by 2.
2.
This is correct, right? So CFX is nothing but this is related to the local fluid friction at a location x, and Stanton number is nothing but Nusselt number divided by Reynolds number into Prandtl's number. This is a group of other dimensionless numbers, and Prandtl number is nothing but characteristic of the flow. So this relates the fluid friction, which is on the right hand side, with the local heat transfer, which is on the left hand side. So that's what Coleman analogy actually is. It helps us.
Prandtl number to the power of 2/3, not 1/3.
2/3. Sorry. Okay. So what happens here is that there are many experimental techniques by which we can measure the fluid friction at certain locations, and we can relate those findings to find out what the heat transfer would be like. So this is the utility of Coleman analogy. Okay. So moving on to question number 3, let me confirm that my slides are visible, right, this time. I hope there are no issues this time like earlier. You can see question number 3. Sorry.
Yes, sir.
Okay. So question number 3 says, what is the expression for local shear stress at the surface of flat plate for the Blasius equation? So let's say we have a flat plate and there is a flow over it, there is a boundary layer formation. For that configuration, what would be the expression for local shear stress using Blasius solution? So there are 4 options given, 4 expressions for local shear stress. The first one is tau w equal to mu into u infinity into under root mu x by u infinity into f double prime naught. Option B says tau w equal to mu into under root u infinity by nu x into f double prime naught. Option C says Tw equal to mu into u infinity under root u infinity by nu x into f double prime naught. Or is it option D, tau w equal to mu into under root mu x by u infinity into f double prime naught?
Answer is B probably.
Okay, someone says B. What about others?
C.
B.
C.
Okay. So we have 2 responses, one in favor of option B, one in favor of option C. Anyone else? Okay, so if you look at the correct solution, the correct answer is option C. So how can we land over here? Let's try to figure that out. So tau omega can be written as minus mu into dou u dou y. So this dou u dou y, this can be written as dou u by dou eta into dou eta by dou y. Now there are certain things that we know. U by u infinity is nothing but f prime, and theta, this can be written as y divided by x by u infinity. So if we come back here, okay, let's do away with the negative sign. That can be taken care by the convention. So dou u by dou infinity. Now u can be written as u infinity into f prime. So if we take a derivative with respect to eta, dou u dou eta, this can be written as u infinity into f double prime, and mind you, this is at y equal to 0, and at y equal to 0, eta also becomes equal to 0. So this would be f double prime at 0, and dou eta dou y, this can be written as 1 by nu x by u infinity. So if we rearrange things a little bit, we can write it as Debjit. So this is nothing but option C. So that's how we can land there. So is the process clear to everyone?
Yes, sir.
So moving on, we'll move on to question number 4. This is also a numerical. So this says that a 2.2 centimeter outer diameter pipe, the outer diameter of a pipe is given. That pipe is to span across a river at a 30-meter wide section while being completely immersed in water. So there is a flow of water, and within that flow there is a pipe installed. The dimensions of the pipe are given, the diameter and the length of it. Now coming to the fluid flow, the average flow velocity of water is 4 meters per second, and the water temperature is 15 degrees Celsius. Now what do we have to determine? We have to determine the drag force in Newton exerted on the pipe by the river. So there are some given quantities as well, like density and dynamic viscosity of water at 15 degrees Celsius are given, rho and mu, and the drag coefficient CD is also given to be equal to 1. You have to figure out the net drag force exerted on the pipe by the flowing water.
So it's total friction force.
Yeah, the total friction force exerted on the pipe by the flow. Let me draw a schematic of this. So there is a pipe like this. Its diameter is given, as well as its length is given, L, and there is a flow like this. Uniform flow, the u infinity, and u infinity is given to be equal to 4 meters per second. The d and L is also given. D is 2.2 centimeters. We can write that as 0.022 meters. And L is given as 30. What we have to find out is the frictional force on it. F is equal to 1. Also, the drag coefficient CD is equal to 1. That is also given. Okay, so the way to solve this is very simple. So frictional, or let's say drag force, correctly like that say, drag force, this can be found out as
0.664 like that.
Uh,
That is
yeah, similarly, no, here CD is given, so we will use that. So this into CD into whatever frontal area of that particular uh, object being obstructed. So this is how CD is defined, right? CD is defined as the drag force divided by half rho u infinity square. So here CD is given, all these other values are given, we have to find out FD. So if we just plug in the values given, so rho is 999.1. This is given in SI units only, so no need to convert. The u infinity is given to be 4, so 4 square, and CD is 1, no issues with that. The frontal area here is, if we take a projection in the direction of the flow, then the cylinder would give a projection of a rectangle. So that rectangle would have the dimensions L into D, and here we know L to be 30 meters and D is given to be 0.022. So now it's just a matter of simple calculation. Can anyone uh, do a quick calculation of this and tell me the answer?
16,572.6.
16,572.6
572.68 newtons.
newtons.
5275.24. 5275.24.
Okay, I'll check this once. What is the value you said, sir? 5.5 what?
5275.
5275. Okay, let's see which one is correct. So I'll do a quick calculation. Please be patient. So 999.1 divided by 2 into 1630 into 0.022. Yeah, so the second one was correct. 5275 point something 25 newtons. This is the correct answer, not this one.
Is it not the frequency area we need to consider here?
Sorry, sir, your
Pi
voice is
dl.
coming very low. Can you come a bit louder?
Sir, is it not a pi dl area we need to consider?
No, not pi dl. Yeah, this is the catch over here. So it's the frontal area, only the projection. So if we look at a rectangular pipe from the direction of the flow, we would be able to see this rectangle only, and this rectangle would have the dimensions of L and D over here. So here if we try to find out the frontal area, that would be L into D, not pi dl, the total surface area of the rectangle.
I have taken pi dl.
Oh.
I have taken pi dl.
Correct. So that's where it went. Okay, so is it clear? Do this.
Yes. Debjit sir, I have a question.
Yes.
Hello.
Yeah.
Rather than making it crossover, now I will make the same cylinder or same pipe in the direction of the river flow. Now what should be my area? It is pi dl?
Which way? Like, I'm not able to.
Now,
Then it is pi by 4 d square.
rather than making it cross now, it is a cross flow na, right now. Now I will make that cylinder along the flow direction.
Along the flow direction. Then the area would be pi d square by 4. This area.
Cross section area.
This
So
area,
cross section area then.
Correct. Okay. That would be the drag force, mind you. Now, apart from drag force, there is a skin friction drag as well. That would be a different issue.
Then pi dl come into picture, no?
Then that pi dl would come into picture. Correct. This is the pressure drag, and that is, or rather the form drag, and that is the friction drag. So there are two different parts of it. And in that case, instead of drag coefficient CD, we would use the skin friction coefficient CF. That might have some different value, and that might give some different value of frictional drag as well. Okay.
Okay.
So moving on, we will move to question number 6. So question number 6 says the ratio of kinetic energy of flow to the boundary layer enthalpy difference is called what? Is it option A Stanton number? Is it B Jacob number? Is it C Ohnesorger number? Or is it D Eckert number? We already have a quick response in the chat. It says option D. Let's see what others have to say.
Eckert number.
Eckert number. Okay, anyone else? If we look at the correct solution, it is indeed the Eckert number. So that is how Eckert number is defined. EC equal to U infinity square divided by the Cp
TW minus T infinity.
So this is the enthalpy difference. And this is a representation of the kinetic energy of the flow. And in case of heat transfer, Eckert number only becomes important if the velocities are very high. But in normal incompressible flows where the pressure difference as well as the related flow velocities are quite low, there we can neglect Eckert number as well as the terms associated with it. The terms associated with it are the material gradient of the material derivative of pressure as well as the viscous dissipation.
Dissipation.
So that's the significance or relevance of Eckert number in convective heat transfer. So moving on to question number 7 of today's session. Question number 7 says the average Nusselt number over the entire plate in case of laminar flow is twice the value of local Nusselt number at the end to the plate. So is this statement true or is it false? So let me try to describe this. So if there is a flow like this and we have x in this direction, so what it says is at the end of the plane, let's say at x equal to L, there is a Nusselt number, a local Nusselt number, as well as there is an average Nusselt number over the entire plane. So if there is over the entire plane, if I calculate the Nusselt number at each location and take an average of it, calling that NU bar. So this says that the average Nusselt number over the entire plane is twice the value of the local Nusselt number at the end of the plane. So average is twice the local. So is this true or is this false?
True, sir.
True. So if I look at the correct answer, yes, it is indeed true. So what happens is, if I take the variation of Nusselt number with x, the variation is of the local one. So this is like this, and let's say if this is L, and this is the value of Nusselt number at x equal to L, and I take the average up until this location L, then that would be half. That would be twice of this value. So this one would be twice that one. Okay. So this was a very simple one. We'll move on if there are no questions. So moving on to question number 8. So for the velocity profile given here, find the ratio of d star delta star by delta, where delta is the displacement thickness and delta is the boundary layer. The velocity profile is given. We have to find out the ratio delta star by delta, the ratio of displacement thickness and the boundary layer.
Hello? Answer may be 5 by 2. 3.
Sorry, I can't hear you.
Answer is C.
Option D. Okay.
No, C, sir. C.
C, 5 by 2. Okay.
Yes.
Okay. So that is one response. Let's see what others has to say.
No, sir. Actually, it is a long calculation, and that is probably sir has given the answer. What is the answer given by sir? Sir, can you repeat?
The answer is not given. I'm just talking about the question up until now. The question is that a velocity profile is given. We have to find out the ratio of delta star by delta. The velocity profile is given as u by u infinity equal to 2 into y by delta minus y by delta square. Okay, so a response in the chat box says it's option A.
Sir, 1 minute. Huh?
Yeah, sure. Take your time, try to solve this.
Sir, answer is 1 by 3.
Okay, so some split is there within the crowd. Someone says option A 1 by 3, someone says option C 5 by 2. We will look at the correct answer. The correct answer is option A 1 by 3. Let's have a look at the solution for this. So delta star, the displacement thickness, this can be calculated as 0 to delta 1 minus u by u infinity dy. Now this u by u infinity is given, so 1 minus 2 into y by delta plus y by delta square into dy. Now if we integrate this, first term will give y, and since it's from 0 to delta, so that would be delta minus 2 by delta into y square by 2, and if we put in delta, so then delta square by 2, so 2 cancels out, 1 delta cancels out each other, and the last term gives, so there is a 1 by delta square, and this becomes y cube by 3, and since it's from 0 to delta, so that's delta cube by 3. So delta cube, and this cancels out, there is a delta cube by 3, and this term is delta, the first term is delta, the second term is also delta, so they also cancel out. As a result, delta star becomes delta by 3, and if I take delta star by delta, then this becomes nothing but 1 by 3. So option A would be correct. Any doubts regarding this? Was it clear? Moving on. We will move on to question number 9 of today's session. Question number 9 says, the higher the value of shape factor, the stronger is the adverse pressure gradient. Is this true or is this false?
True.
Okay. Let's wait for other responses. Anyone else has anything to say? What do you think? The higher the value of shape factor, the stronger is the adverse pressure gradient. Is it true or is it false? Okay, so if we have a look at the solution, it is indeed true. The shape factor is given by the displacement thickness by the momentum thickness, and the higher the value of shape factor, the more turbulent the flow becomes, and in those cases, the chances of a higher adverse pressure gradient and flow separation, that goes on increasing. Okay, so this is how shape factor can determine the nature of the flow in certain situations. now we'll move on to last question of today's session. So the last question says, for the velocity profile u by u infinity equal to y by delta, find the shape factor. Okay, so here is a little bit of a misprint. So h will be written as delta star by theta. So the ratio of displacement thickness to momentum thickness. So what would be the value of this? You can take your time, try to solve this one. Pick the correct solution. There are 4 options. Option A says 5, option B 0.3, option C 3, and option D 0.5. The velocity profile is very simple. It's a linear profile. U by u infinity equal to y by delta. So the correct process would be to find out delta star first, then theta, then take the ratio of it and find out whatever value this comes out.
Sir, give some time.
Yeah, sure. Please take as much time. Okay, so we have a one response that says it's option C.
Answer is 3.
Answer is 3. Okay. And answer is indeed 3. So we will quickly have a look at how to solve this. So delta star displacement thickness is 0 to delta 1 minus u by u infinity integrated over dy. So if we plug in the values over here, 1 by 1 minus y by delta integrated from 0 to delta, this becomes y minus y squared by 2 delta from 0 to delta. So plugging in those values, it becomes delta minus delta squared by 2 delta. Things out, it becomes delta by 2. And similarly, if we try to find out the momentum thickness, then it would be 0 to delta u by u infinity into 1 minus u by u infinity, and plugging in the values, there will be y by delta minus y by delta whole square integrated over dy. And if we perform the integration over here, so y square by 2 delta, and this becomes, there is a delta square here, and this becomes y cube by 3 from 0 to delta. And if we simply plug in those values, so this becomes delta square by 2 delta minus delta cube by 3 delta square. These things out, it becomes simply half minus 1/3 into delta, and that is half minus 1/3 is nothing but 1 by 6. So this becomes delta by 6. Now if we simply take the ratio of them, the answer is 3. So everyone got this one correct. Okay, so any doubts regarding this solution? If not, then that brings us to the close of today's session. Thanks a lot.
Sir, one question is there.
Yes, please.
Just 1 minute. I'm going to. Actually, in assignment 1, I got one answer wrong. So, related with it. Actually, it was very simple, but how I missed. Which of the following assumption is not valid for Fourier's law of heat conduction?
Okay.
No heat generation, it is very straightforward. It is assumption. Then constant thermal conductivity, that is isotopic material, that is assumption. And third option I selected, and no time required for heat to propagate through media. And option D is none of the above.
Okay.
And correct answer is none of the above.
Okay.
I have clicked on answer C. No time required for heat flux to propagate through media. So I want clarification related with it.
Clarification regarding. Okay. So the thing is, in Fourier's law, the transience is not taken into account. We simply assume that the
It's a steady.
the setting up of a pressure temperature gradient that is instantaneous, that does not take any time. So for example, if I do a little scribbling here, let's say we take a metal rod like this. It's at a there is T infinity, and this entire metal rod is also at T infinity, and suddenly we start heating it with a candle, which is at a higher temperature, let's say anything, let's say T hot. So what Fourier's law so what would actually happen in reality? In reality, this part closest to this location of heating, that would heat up at first, and then there would be a gradual propagation of the heat of the temperature gradient downstream, and finally a uniform temperature gradient would set up, right? But what Fourier's law takes into account is simply that Q equal to K into dou T dou X, right? Correct. So this is heat transfer per unit area, that is minus K into dou T dou X. So here this temperature gradient dou T dou X, Fourier's law assumes that this X, and if we take T over here, so TH to the temperature, let's say T infinity, this temperature gradient, my figure is not perfect, so this temperature gradient, this sets up instantaneously at T equal to 0. Whereas in reality, what happens is something like this. Let me try to draw this correctly. Here is T. So initially the entire rod is at T infinity, and once it starts heating, so okay, so here the gradient is like X. I'm taking in this direction. So at X there would be the maximum temperature. What happens is initially this part heats up. Initially this part heats up, and then slowly this temperature profile develops over time, and finally it becomes a uniform temperature profile, and this gives us the required dou T dou X. This takes some finite amount of time in reality, but Fourier's law, this assumes that this temperature gradient, this is set up instantaneously as soon as some heating or temperature is provided at any location. Does that clear things up?
Yes. Okay. Actually, that was little thinking.
Hello, sir.
And one more.
Hello, sir.
Yes, please go ahead.
Am I audible?
Yeah.
Sir, actually in Fourier's law, there is one assumption that constant thermal conductivity. So the constant thermal conductivity with respect to what? That means it's respect to time or it's respect to space?
Both. This K,
Okay.
the
So sir,
thermal conductivity, this K is neither a function of x nor a function of time. K is a
okay,
constant.
sir. Actually, okay, sir. Sir, actually, in some book, it is also mentioned that the K may be variable with respect to space, but
Yeah,
there's not so much effect on of it.
correct. So there are many situations in which K is either a function of x or even K is a function of the temperature itself. So as the temperature changes of a certain material at a location, its thermal conductivity also changes. So this happens in
Yes, sir.
many
Yes, sir.
situations, but for simple analysis and most general engineering cases as well, this thermal conductivity is taken to be constant rather than a function of either space, time, or temperature.
Okay, sir. Thank you,
Okay.
sir.
But there can be situations in which K is a function of those. Okay.
Yes.
Sir,
Yeah.
hello.
Yeah. Please go
Sir,
ahead.
this boundary layer concept is applicable for high Reynolds number. Actually, it is given greater than 100 something.
Correct.
Okay. So, boundary layer, this concept, boundary layer equations are applicable for laminar flow as well as turbulent flow, both.
Yeah. In our course, we are dealing with laminar boundary layers only, but there is theory related to turbulent boundary layers as well.
Yes, means it covers both.
Yeah, it covers both. Boundary layer, what does it mean? It means that there is a solid boundary within a flowing fluid or in some contact with it, and within that flow there is some effect of that boundary, and that region we call it as a boundary layer, and we try to study it.
Because why I have confused with it, turbulent flow, because high Reynolds number there is a flow separation. Okay,
Yeah, correct. No, see,
correct. Then again that assumption says that there should not be a flow separation under boundary layer.
true.
So that's why.
The thing is like this, if we draw the full scale thing, that there is a u infinity coming from this edge and there is a flat plate over here. So initially the flow is laminar, and there, this is where, this is the location that we deal in, the laminar boundary region. Then comes a region where a transition occurs. So here the flow keeps switching between laminar and turbulent, and finally it becomes fully turbulent. And within that turbulent zone also there is a sub layer which is laminar.
Yeah.
But we restrict our discussions up until here, the laminar one.
But equations are there for turbulent flow also.
There are equations and theory there as well.
Yes, yes.
This is where it becomes turbulent. Okay. Anything else? Okay, before I forget, last day you had asked that both Nusselt number as well as Peclet number, these are both told as the ratio of convective heat transfer to the conductive heat transfer, right? But then what is the
Conductive heat transfer.
then what is the need of them separately? So Nusselt number, this actually is related to the finding out of this H. This H is not known in most cases, and this has to be either experimentally or somehow theoretically determined, and that's what leads to engineering design and further understanding of the systems as well. So this is the significance and relevance of Nusselt number. On the other hand, Peclet number is also similar to this, but Peclet number is actually a class of dimensionless numbers. We study Peclet number with respect to heat convection only, or with respect to heat transfer only. But Peclet number has other uses in mass transfer, mass diffusion, and advection as well. So that comes from a different philosophy, that says that it's the ratio of these rates of advection and diffusion. So advection of in a special case, in case of heat transfer, then advection of heat is convection and diffusion of heat is conduction. So that's what Peclet number represents, or that's what its significance is. Okay.
Okay, sir.
So thank you all. We will meet again next week, next Tuesday from 6 to 7, this time slot only. Goodbye until then. Thanks a lot for today's